July 1st, 2025. Astronomers spot something streaking into our solar system at over 130,000 miles per hour, and its path breaks every rule of gravity we trust. 3. I/Atlas isn't just another comet, it's an interstellar behemoth, the third of its kind ever seen, but brighter, bigger, and weirder than any before. In weeks, it grows a coma larger than Earth itself and a tail tens of thousands of kilometers long, while its chemistry makes no sense and its orbit refuses to behave. Are we looking at a new class of cosmic visitor? Or at something we can't explain at all? Here's how scientists realize this isn't just defying gravity. It's rewriting what we thought was possible. In the pre-dawn hours of July 1st, 2025, a handful of astronomers at the Atlas Survey Telescope in Chile watched their screens as a new object appeared in the data stream. At first, the numbers looked like a glitch, an object streaking across the starfields at nearly 61 kilometers per second, far too fast for any known comet or asteroid from our solar system. The software flagged its orbit as hyperbolic, a mathematical signature that means it isn't bound to the sun. This was no ordinary visitor. Slack messages from the control room lit up with disbelief. One read simply, "This can't be local. We've got an interstellar incoming. Flag it." Within minutes, the team was coordinating with the Minor Planet Center and messaging colleagues around the world. The initial coordinates placed the object in the dense star fields near Sagittarius, making it hard to spot in earlier images, but as the data poured in, it became clear. This was the third confirmed interstellar object ever detected, and it was already on a trajectory that would never bring it back. The overnight shift, usually routine, had become historic in a matter of minutes. The object's speed, over 130,000 miles per hour, meant it had sailed in from deep space, untouched by the sun's gravity. The discovery logs captured the sense of awe. A cosmic messenger, larger and more active than anything seen before, was now racing through the solar system. The need for rapid orbit calculations became urgent. Every minute mattered, as astronomers scrambled to alert telescopes worldwide. The hunt was on, not just to track its path, but to understand what it was, where it came from, and what secrets it might carry from the galaxy beyond. Most objects that pass through our solar system are held in check by the sun's gravity, tracing out gentle ellipses or wide ovals that bring them back again and again. But 3I/Atlas charts a course that breaks this pattern entirely. Its orbit is hyperbolic, a mathematical curve that never closes, a one-way ticket from the depths of interstellar space. The defining number here is eccentricity. For a bound orbit, like Earth's, eccentricity sits just above zero. Even the most stretched-out comets rarely exceed an eccentricity of 1. Atlas, by contrast, carries an eccentricity of approximately 6.08. At this value, the path is so open it's almost a straight line, slicing through the solar system and never looping back. Calculating such a trajectory is no small feat. Teams at the Minor Planet Center and observatories worldwide fed every new position into orbital models, refining the numbers with each update. The results were unambiguous. At a speed of nearly 61 kilometers per second, and with that staggering eccentricity, Atlas is unbound. Gravity's grip is simply too weak to slow it down. This isn't a close call or a matter of interpretation. The mathematics of orbital mechanics leave no room for doubt. No matter how many times the numbers are checked, the outcome is the same. Atlas is just passing through, and nothing in the solar system can hold on to it. The next step was to chart its path, to predict where and when it would sweep past the planets, and to mobilize the world's telescopes for a fleeting chance to study this cosmic outlier before it vanishes into the dark. Precise timing is everything. When tracking a visitor, like 3I/Atlas, its one-way journey through the solar system is mapped out by 4 critical encounters, each a narrow window for science before it vanishes. The first milestone arrives on October 3rd, 2025, when Atlas sweeps past Mars at a distance of just over 31 million kilometers, or about 0.21 astronomical units. For planetary scientists, this is the closest pass to a major planet and a rare chance for orbiters around Mars to capture high-resolution images of the coma and tail. Just weeks later, on October 29th, the object reaches perihelion, its closest approach to the Sun, at 1.36 astronomical units, still nestled inside the orbit of Mars. Here, solar heating peaks and any buried ices or volatile gases are most likely to erupt, driving changes in brightness and activity that telescopes worldwide scramble to record. The pace doesn't slow. By November 3rd, Atlas passes near the orbit of Venus, offering another fleeting opportunity for observation, though at a much greater distance than the Mars flyby. Then, as it races outward, the object makes its closest approach to Earth on December 19, 2025, at about 1.83 astronomical units, roughly 274 million kilometers away. Even at its nearest, Atlas remains far beyond the reach of amateur telescopes, its faint glow a challenge for even the largest observatories. Each of these dates is more than a waypoint. They define the only moments when sunlight, geometry, and distance align for the world's instruments to probe its chemistry, dust, and motion. For astronomers, missing a window means losing answers forever. The urgency is real. Atlas will never return. Every observation is a race against time, as this cosmic interloper continues its silent, irreversible plunge back into interstellar darkness. Pinning down the true size of 3I/Atlas has become one of the most stubborn puzzles in modern astronomy. Its nucleus, the solid core buried beneath layers of gas and dust, remains hidden from direct view, masked by a faint glow that hovers at magnitude 14 or dimmer. Even the largest ground-based telescopes equipped with adaptive optics struggle to separate the core from the surrounding haze. Early estimates, drawn from photometric modeling and high-resolution imaging, span an extraordinary range. Some measurements with the Hubble Space Telescope suggest a compact nucleus, just 320 meters across, barely the length of 3 city blocks. Other analyses, using stacked exposures and careful coma subtraction, point to a much larger object, perhaps 5.6 kilometers wide, or even 11 kilometers by some ground-based calculations. A few experts, including Professor Lowe, have argued that if Atlas were a solid, inactive body, its faintness could hide a nucleus up to 20 kilometers in diameter, larger than any interstellar object ever seen. But the reality is far less certain. The faintness of Atlas, even at its brightest, means that every estimate is tangled in assumptions about its reflectivity, surface texture, and the density of its shrouding coma. Astronomers must model how sunlight scatters off dust grains and how much light escapes from the hidden core. Each parameter introduces new uncertainties, and small changes can swing the size estimate by orders of magnitude. The result is a portrait painted in shifting shadows, a nucleus that could be a modest chunk of ice or a true cosmic giant. For now, the only certainty is uncertainty itself. As the world's telescopes continue to collect data, the hope is that a rare moment of clarity, a brief lull in the surrounding dust, a lucky angle, will finally reveal the heart of this interstellar wanderer. Until then, every observation is a wager against the unknown, and the true scale of Atlas remains just out of reach. Surrounding the hidden nucleus of 3I/Atlas, a vast envelope of gas and dust began to expand almost as soon as it entered the inner solar system. By July 2025, the coma, this ghostly shroud, measured an astonishing 26,400 kilometers by 24,700 kilometers, as recorded by the Gran Telescopio Canarias. That's nearly twice the diameter of Earth, and it continued to grow as sunlight drove more material from the object's surface. The dust tail, first a faint streak, lengthened rapidly, stretching beyond 56,000 kilometers by late August, a ribbon of fine particles swept back by solar radiation and the solar wind. But these numbers only hint at the true scale. Infrared observations from NASA's SPHEREX mission revealed a carbon dioxide halo extending over 340,000 kilometers, dwarfing even the coma itself. As Atlas approached the Sun, The color of the coma shifted, a deep, dark red at first, trending towards green as new ices sublimated and chemical reactions took hold. This transformation wasn't just a matter of temperature. It spoke to the complex chemistry locked within the object, now exposed for the first time in millions or perhaps billions of years. Tracking these changes required both the world's largest telescopes and a global network of amateur astronomers. While professionals captured high-resolution spectra and images, citizen scientists, some working from backyard observatories, helped monitor the evolving shape and brightness of the tail. The Atlas Hunters Group, a loose coalition on Discord, provided real-time updates and even flagged new features before some observatories could respond. Their combined efforts allowed for continuous monitoring as Atlas raced across the sky, ensuring every surge in activity was logged and every fluctuation in color and structure was noted. In this way, the expanding coma and tail became not just a scientific target, but a living record of collaboration, evidence of how a single cosmic visitor could unite the eyes of a planet. In early September 2025, a new feature began to puzzle the global network of observers tracking 3I/Atlas. Amid the expected sweep of dust trailing away from the sun, amateur astronomers started to notice something that didn't fit the standard cometary blueprint. A faint, narrow ribbon of dust stretching sunward, seemingly defying the solar wind. The first confirmed image came from Madrid, where 17-year-old Clara Segovia, working with a modest backyard telescope, captured a sequence showing a distinct anti-tail, a dust feature pointing directly toward the sun rather than away. Within hours, her post on the Atlas Hunters Discord lit up with excitement, and professional teams scrambled to verify the phenomenon. Unlike the classic tail, which forms as sunlight, and the solar wind pushed dust and gas outward, an anti-tail appears only under rare geometric alignments. It's not a physical jet shooting sunward, but a trick of perspective. Larger, heavier dust grains, released weeks earlier, drift along the comet's orbital plane. When Earth crosses that plane, these grains seem to stack up into a thin, sunward spike. For Atlas, the anti-tail's sudden appearance in September was a clear sign of complex dust dynamics at work, evidence that the comet was shedding material in ways that standard models struggle to predict. Citizen scientists played a crucial role in tracking the anti-tail's evolution. Night after night, amateur imagers across Europe and Asia logged its changing angle and brightness, feeding data into central repositories accessed by professionals. Their collective vigilance allowed astronomers to map the timing and structure of the anti-tail in unprecedented detail, revealing subtle shifts that hinted at bursts of activity from deep within the nucleus. In the story of 3I/Atlas, this fleeting sunward feature became more than a curiosity. It was a window into the chaotic, unpredictable physics of interstellar dust, and a reminder that sometimes the rarest discoveries begin in the hands of those watching from their own backyards. Infrared spectroscopists, working through the early weeks of August, began to untangle the molecular inventory of 3I/Atlas. What they found was unlike anything seen in solar system comets. The near-infrared data, especially from NASA's SPHEREx mission, revealed a massive halo of carbon dioxide gas, stretching over 340,000 kilometers from the nucleus. That's nearly the distance from Earth to the Moon, and it dwarfs the already enormous coma mapped in visible light. But the true surprise lay in the ratios. For every molecule of water vapor detected, there were about 8 molecules of carbon dioxide. In comparison, typical comets from our own solar system have water as their dominant volatile, with carbon dioxide trailing far behind. Here, the script is flipped. Atlas is powered by a chemistry that's almost alien, its activity driven by an abundance of carbon dioxide rarely seen even in the most distant solar system objects. This imbalance is more than a curiosity. Such a high carbon dioxide to water ratio hints at an origin in a cold, carbon-rich environment, possibly far beyond the carbon monoxide snowline of any star system. Alongside the carbon dioxide, near-infrared spectra picked up faint signatures of cyanide compounds, molecules that are toxic on Earth but common in the chemistry of deep space. Each detection adds a layer to the puzzle. Is Atlas a fragment of a planetesimal forged in an ancient carbon-heavy disk? Or has its chemistry been transformed during eons adrift in interstellar space? For the spectroscopists, every new scan is a step into the unknown. The volatile inventory of Atlas doesn't just challenge old models, it demands new ones, opening a chapter where the drivers of cometary activity are rewritten by the chemistry of another star. High-resolution spectrographs trained on 3Y/Atlas began to reveal a chemical fingerprint that left even seasoned comet specialists unsettled. As the comet's coma spread outward, teams at the VLT and Hubble Space Telescope focused on the faint, telltale glow of atomic metals. The expectation was simple. In nearly every known comet, nickel and iron appear together, forged in the same stellar nurseries and locked side by side in icy grains. But the spectra from Atlas told a different story. Repeated exposures stacked over long nights picked up narrow emission lines at wavelengths matching atomic nickel, especially the 3,414 and 3,482 angstrom bands. These signals, faint but persistent, stood out against the noisy background of dust and sunlight scattered through the coma. Yet when analysts searched for iron, the usual companion, they found nothing. The classic Fe1 and Fe2 lines, typically as strong as nickel in solar system comets, were absent, even in the deepest stacks. Upper limits placed iron at least 10 times weaker than nickel, a ratio that defies the chemistry of our own planetary neighborhood. Some argued for caution, pointing to the challenges of extracting clean signals from such a faint, dusty object. Others insisted that the nickel-rich, iron-poor signature was real, a hint that Atlas was assembled in an environment far stranger than anything familiar. The debate spilled into late-night conference calls and preprint archives, with every new spectrum scrutinized for artifacts and errors. For now, the metal lines stand as a puzzle, a chemical riddle woven into the light of an interstellar traveler. The next step, polarimetry and dust studies, searching for clues in the way Atlas scatters and polarizes starlight, hoping to tie the metallic anomaly to the physical structure of its grains. Material scientists and astronomers turned to polarimetry to probe the dust grains released by 3Y/Atlas, a technique that measures how sunlight scatters and polarizes as it passes through the coma. The results were striking. Unlike the dust from most solar system comets, which tends to reflect light in distinctive ways tied to their icy, compact origins, Atlas's dust showed a polarization signature more reminiscent of the outermost reaches of our own planetary system. The data pointed to grains that are both highly porous and rich in dark, carbon-based compounds, a profile closely matching the icy, organic-laden debris found among trans-Neptunian objects. Teams at the Gran Telescopio Canarias and the VLT compared Atlas's polarization curves to models built from laboratory analogs, ultra-fine carbon mixed with water ice, pressed into low-density, fluffy aggregates. The fit was almost uncanny. Light scattered at the same angles, and the degree of polarization tracked precisely with what you'd expect from a body assembled in the coldest, darkest zones of a protoplanetary disk. This suggests that Atlas's dust was never compacted by intense heat or pressure, but instead preserved the fragile structure of its birth environment, far from any star. For planetary scientists, these findings add a crucial piece to the puzzle. The dust structure and composition hint at a formation story that predates the solar system, connecting Atlas to a lineage of objects forged in the outer darkness of other worlds. As the debate over its true nature intensifies, the dust grains drifting from its coma serve as silent witnesses, carrying the memory of a place and time utterly alien to our own. Night after night, astrometry teams at observatories worldwide locked onto 3I/Atlas, measuring its position against the background stars with every possible tool at their disposal. Each new data point was fed into orbital models, searching for the smallest sign that this object might be straying from a gravity-only path. The process demanded extraordinary precision, milliarc-second accuracy, because even the slightest deviation could hint at forces beyond what physics predicts. Yet the challenge was immense. Atlas's nucleus was shrouded in a bright, shifting coma, making it nearly impossible to pinpoint its true center. Hubble's July 2025 imaging campaign, using advanced coma subtraction algorithms, squeezed residuals down to just 20 milliseconds, but uncertainties from dust and gas still loomed large. As the weeks passed, the Minor Planet Center, Rubin Observatory, and the Zwicky Transient Facility pooled their results, comparing hundreds of images. The numbers told a consistent story. Every measured position, within the limits of current technology, matched the predictions of Newtonian gravity. No statistically significant non-gravitational acceleration appeared in the data. The official orbit solutions, updated by JPL and the MPC, showed residuals well within the envelope set by measurement error and coma modeling. Even when independent analysts combed through raw images, hunting for outliers, any apparent discrepancies dissolved under closer scrutiny. Still, the stakes remained high. Any real deviation, even at the edge of detectability, would demand an explanation: outgassing, fragmentation, or something more exotic. For now, the evidence is clear. Atlas's path, as tracked by humanity's sharpest eyes, hews to the rules of gravity alone. The mystery, for the moment, lies not in where it travels, but in what it carries and how it was made. The scientific debate over 3Atlas has become a high-stakes contest of ideas, with every hypothesis tested against a growing mountain of data. On one side, planetary scientists argue for classic cometary mechanisms. Internal outgassing, driven by sunlight, could nudge the object's path. They point to the volatile-rich coma, the rapid dust production, and the possibility of sudden fragmentation. If the nucleus is as fragile as polarimetry suggests, even minor outbursts might create enough thrust to explain subtle orbital shifts. Yet critics note that no abrupt trajectory jumps or visible fragments have been detected, and the observed activity seems too modest to account for any large-scale deviations. A second camp focuses on the structure of the nucleus itself. Laboratory models and dust polarization data hint at a low-density porous core, a fluffy aggregate that could amplify the effects of even gentle outgassing. In this scenario, Atlas is less a solid rock and more a loosely bound cloud of icy grains, easily jostled by its own escaping gases. This idea fits the observed dust properties, but struggles to explain the consistency of its motion, especially given the lack of measurable non-gravitational acceleration in astrometric data. Then, there are the more speculative voices. Professor Lowe, known for pushing boundaries, has argued that if the size and brightness estimates hold, and if unexplained orbital changes persist, natural explanations might not be enough. She points to the faint possibility of an artificial object, perhaps a derelict solar sail, engineered to harness sunlight for propulsion. While most of her peers dismiss this as premature, the controversy has reignited memories of the debates over Oumuamua. Others suggest entirely new physics, interactions with the interstellar medium, or forces not yet described by current models. For now, the field remains divided. Each model is tested, challenged, and revised as new data arrives, and the only consensus is that Atlas refuses to fit neatly into any established category. Across the globe, a coordinated campaign swung into action to capture every possible detail from 3Atlas's brief visit. Time on the James Webb Space Telescope, normally scheduled years in advance, was urgently reallocated for 2 windows in September and October, with NIR specs set to probe the object's infrared chemistry at the highest possible sensitivity. Hubble, meanwhile, devoted a series of ultraviolet and optical imaging sessions, pushing its detectors to the limit to resolve the inner coma and hunt for signs of jets or fragments. On the ground, Gemini South and the Very Large Telescope tracked the object's changing brightness and polarization, mapping dust properties night after night. The Gran Telescopio Canarias, with its massive mirror, monitored the evolving coma size and tail structure in visible and near-infrared light. The Vera C. Rubin Observatory, still in commissioning but already a powerhouse for transient detection, ran high-cadence astrometric sequences to refine the orbit and catch any subtle deviations. Each observatory fed its data into a central repository, enabling real-time cross-checks and rapid response to unexpected changes. When 3D/Atlas swept past Mars on October 3rd, controllers at JPL executed last-minute reprogramming of the Mars Reconnaissance Orbiter, pushing its imaging payload to capture the closest-ever snapshots of an interstellar visitor's coma and tail from orbit. MAVEN, another Mars orbiter, tuned its spectrometers to sniff out faint traces of exotic gases, hoping for a glimpse of chemistry never before sampled in situ. This was more than a routine campaign. For a few critical months, the world's most advanced astronomical instruments, space-based and ground-based, professional and amateur, were synchronized in a blitz of observation. Every wavelength, every vantage point, every fleeting opportunity was seized. The goal? To build a complete, multidimensional portrait of Atlas before it slipped back into the darkness between the stars. The discovery of 3D/Atlas stands on the shoulders of two earlier interstellar visitors that shook the foundations of planetary science in the last decade. Back in October 2017, astronomers at the Pan-STARRS Observatory in Hawaii spotted a faint, tumbling object racing through the inner solar system. Named 1I/Oumuamua, it was unlike anything seen before, small, about 200 meters long, with no visible coma or tail, and moving so fast that the sun's gravity could never reclaim it. Its brightness flickered erratically, hinting at a bizarre, elongated shape, and its path showed a subtle acceleration that defied easy explanation. Some researchers, including Professor Lowe, even raised the possibility of an artificial origin, a solar sail drifting between the stars. The debate over Oumuamua's true nature remains unresolved, its secrets locked away as it sped back into interstellar darkness. Just 2 years later, in August 2019, the sky delivered a second surprise. Amateur astronomer Gennady Borisov, scanning the dawn from Crimea, identified a bright, fuzzy point that soon revealed a classic cometary tail. 2I/Borisov was confirmed as interstellar by its hyperbolic orbit and high velocity, about 33 kilometers per second. But Borisov's behavior was a study in contrasts. It looked and acted like a textbook comet, shedding dust and gas as it neared the sun, its chemistry matching the volatile rich ices found in the outer reaches of our own solar system. Where Oumuamua was mysterious and silent, Borisov was familiar and noisy, a comet by every measure, but its origin. These two cases set the stage for 3Y/Atlas. Oumuamua challenged ideas about shape and propulsion. Borisov showed that interstellar objects could mimic the comets we know. Now with Atlas, astronomers confront a visitor that combines extremes, larger, more active, and chemically stranger than either of its predecessors. Each arrival has forced science to redraw the boundaries of what's possible. And with Atlas, the story of interstellar wanderers enters a new, more perplexing chapter. Across the astronomical community, the question of where 3I/Atlas truly comes from has become a kind of cosmic riddle. Its hyperbolic path and staggering speed leave no doubt that it is an interstellar traveler. But tracing its story back to a single birthplace is another matter entirely. Some theorists look to the Milky Way's thick disk, a vast, ancient population of stars and debris, billions of years older than our Sun. The thick disk is a relic of the galaxy's turbulent youth, a region shaped by mergers and supernovae, rich in heavy elements and cosmic dust. If Atlas formed there, it could be carrying material forged before Earth itself existed, a frozen record of processes that shaped entire generations of stars. Yet the evidence remains tantalizing, but incomplete. Models suggest that only an object ejected at high speed from a dynamically hot, chemically exotic environment could arrive with Atlas's velocity and strange chemistry. Its high carbon dioxide content, hints of nickel-rich dust, and the dark porous grains all fit the profile of a body sculpted in the cold outskirts of an ancient system, perhaps one that never knew the warmth of a stable, sun-like star. But without isotopic fingerprints or a precise galactic trajectory, these remain working hypotheses, not certainties. For scientists and philosophers alike, Atlas becomes more than an object. It's a messenger. Professor Lowe, never one to shy from speculation, calls it a cosmic postcard, possibly older than Earth, sent across light years to land, by chance, within reach of our telescopes. Whether it's a fragment of a shattered exoplanet or just another icy wanderer, the questions it raises are as important as any answer. What other chemistries, what other stories are carried by the debris between stars? And as we watch Atlas disappear into the night, we're left to wonder, how many more messengers have come and gone, unnoticed, in the long history of our galaxy? On July 1st, 2025, the Atlas survey in Chile recorded the unmistakable signature of 3I/Atlas, marking our third confirmed interstellar visitor. Its hyperbolic trajectory, with an eccentricity near 6.08 and speed over 57 kilometers per second, proved it would pass through the solar system only once. Observations revealed a faint nucleus between 320 meters and 11 kilometers across, an enormous coma over 26,000 kilometers wide, and a rapidly growing dust tail. Chemical analysis detected an unusually high carbon dioxide to water ratio, traces of cyanide, and nickel emission without iron, features not seen in typical solar system comets. Yet despite global campaigns using the James Webb Space Telescope, the Hubble Space Telescope, and Mars orbiters, questions remain. The cause of its orbital deviations and the true nature of its composition are still debated. With each document and image, 3I/Atlas stands as evidence that our understanding of interstellar objects is incomplete. Its journey challenges current models and offers new data for the next generation of research.